it's not, of course. Oh, yes, it is now. Good. Okay. So friction opposes motion, and it's always got a vector direction opposite motion. It converts the energy into the mechanical energy of that motion into heat energy. You can tell you keep your hands up when you rub them together because of friction. Friction is caused because no surface is perfectly smooth, right? I mean, this board feels very smooth, this board feels very smooth, but in reality, on a molecular level, the molecule's surfaces, the surface of the board, is really covered in little bumps and grooves, right? When I run my finger or another object across this board, my finger has quite visible and obvious, even not at the molecular level, bumps and grooves. And when one surface slides across another surface, those bumps and grooves fall into each other, collide, and just like if I was going along here and bumped there, maybe I'd have the energy to keep going, but it would slow me down. Friction comes from that. Friction also comes because you know, even though we haven't gone there yet this year, that everything is made up of atoms, and atoms have tiny little positive charges called protons in the nucleus at the center of the atom, and neutrons also, which have no charge. So we've got some protons, some neutrons, and they have electrons, which orbit, not exactly like a planet, but they orbit the nucleus, and electrons are negatively charged. So all these surfaces have little charges, and we know that negative charges repel negative charges, positive charges repel positive charges, and opposite charges, a negative and a positive, attract each other. So you have these little positive and negative forces attracting and repelling each other whenever surfaces move past one another. And those attractive and repulsive forces are really called electrostatic attractions and repulsions, and they are also a contributing factor to friction. So, we know that friction's a reality. If it weren't, we'd just keep moving in a straight line forever, according to Newton's first law. So, friction depends on mass. Things with larger mass experience larger amounts of friction, right? So since it's twin day, let's say two of us were wearing the exact same skirt, and let's say my daughter, who refused to be a twin with me today, was sitting here, and she was sitting on the same surface, and her mass was 20 kilograms less than mine. Will be nice. And her skirt and my skirt had the same friction with the same chair that we're sitting on. And we both tried to move forward. Who would experience more friction? Me, because my mass is larger. So mass is something that affects friction. Friction is also affected by whether the object is currently in motion or currently at rest. We know that when something is at rest, the coefficient of friction between the two surfaces at rest in relation to each other is larger than when the thing's already moving. It takes more force to get something to start moving than it takes to keep it moving once it's already moving. And we talked last week about how, like, when you're biking slowly into a pothole, you go down in there and it has more of an effect than if you can just zoom right over the top of the pothole. The same thing applies to friction. And I could use this tub even to kind of demonstrate. Let's see, this is a 1 Newton force meter, and this, what's it 20? Maybe I want a 5 or something. That's a 5. That's a 5. I don't know which one will work best for this tub. But let's say all this stuff in the tub has the same mass, right? Will you aim for me? Just kind of, okay. So, probably I'll try the 5 first. Let's see. So let's say, is it going to be difficult? Maybe. Okay. How much force does it take to get this thing moving? About 2 newtons. And to keep it moving at a constant pace, it takes about 1.5 Newtons. So if I do it again, you watch the force meter. To get it moving, takes just a little more than it takes to keep it moving once it starts moving. I wonder if we can see better on this one. Because, of course, this force meter has less of a range, but we can build it a little colder. I hope it's not going to stick, is it?
I feel like it's been over.
I could put it over. I know if you're facing down, that would be problematic.
And then there's a way you can switch it.
Yes, we can switch it. There's stupid. Okay, common sense prevails. Maybe we'll just attach a few more pliers. A pair of pliers. Oh, I've done that. I had a pair of pliers. That might be nice. Okay. Okay, so, it's going to give a little bit, which could be bad. Alright, so to get it moving, it's not going to work. So you have okay, moldable eraser. Excellent. There's always a way. Alright, so, at a chemistry class, have to grade the lab with once. Oh, this is a 20 Newton. I don't like the 20 Newton. I want the 1 Newton. Oh, there it is. Okay. That's not going to be good. Oh, I messed with the 1 Newton. Okay. So, to get it moving, I'm basically bottoming it out. Yeah, to keep it moving, I am too. So I guess the 5 is kind of what I'm stuck with. I'll do it in front of you guys and then in front of them. So, if I have this 5 Newton scale, I wish I had a 2 Newton scale, to get it moving, static friction is going to take more force than to keep it moving. So, if I can keep it moving at a constant pace is good. So watch again. Hopefully you can see that to get it moving takes more force than to keep it moving. Yeah, to get it moving, it takes. This quarter here. Okay. To get it moving. Look again. And you see that it's just a little less to keep it moving than to get it moving. It's really hard to see. So here, lean forward. So to get it moving is going to be about 1.5 Newtons, but to keep it moving is like a little less than that. It's really, really hard to see, sorry. So to get it moving, and once it's moving, it backs off from 1.5 Newtons a little bit. So just a quick way to hopefully confirm that static friction is more than kinetic. Yes. So kinetic friction, once something is moving, it experiences a little less friction with the same surface than it experienced when it was just trying to get moving. Static friction is more than kinetic friction. So we talked about mass affecting friction, we talked about whether the thing is moving or not affecting friction, and also the actual two surfaces, like say the surface of the wood versus the surface of this Play-Doh in plastic, is going to have a different amount of friction than the wood with this little block or the wood with this metal battery here. So, make a prediction. Which one do you think will have more friction?
Can we feel them?
Sure. I need the people here in the middle. Ooh, work board.
The one in the middle.
See the board?
I mean, the one in the middle will have less friction.
You think the wood on the wood will have less friction?
No, I'm sorry, I'm wrong. I think that have less friction.
Okay, so you think this will have the least friction?
I actually think the
No, I think
the
it'll have
wood-
have more friction.
I think it's the wood.
Okay, so how can we tell which one will have less friction?
Experiment.
We're going to experiment. So what kind of experiment will tell us which one will have less friction?
That end of the board up. I'm waiting to see which one starts to move first.
Right. So that'll test out this coefficient of static friction, and actually it's a really easy calculation to actually get the number for the coefficient of static friction this way, but I'll teach you that another year. So you pick up the end of the board. Which one's going to move first? It's experiencing the least amount of friction.
That's the battery because it's slicker.
So the two surfaces just have less interaction. And then the clay.
Yes, we were right. Then the block wood.
So will it be the same each time? Yeah, it should be the same each time. So if we did it again, it should be the same. Battery first, and then Play-Doh. Oh, and then wood finally. Then the book has an experiment where you do that, and then you sand down the board, but nobody will be all that if I sand the board down in the room, making a big bunch of dust and mess. So we're just going to use foil. So if I change the two surfaces that are in contact, am I going to change the amount of friction? All right, so I've changed the surfaces from wood and the other materials to foil and the other materials. So do we think that the board will go as high before the things start moving? No. So you think this will have less friction
Yeah.
than... Do you think they'll go in the same order that they went before?
Yeah.
9 volts, then Play-Doh, then...
Yeah, the battery went first last time.
Battery went first last time.
Then the Play-Doh.
Going to go first this time.
Think the wood's
I
going to
think
go
the
first?
Play-Doh
Wood will go
So-
second.
Play-Doh.
So you're like, okay, we saw metal on wood. This is metal on wood. What's going to go first? I can see your reasoning. I'm going to hold the foil though, just in case. So we're higher already than we were the first time. Battery first, then Play-Doh, but pretty quickly after that wood. The battery and the Play-Doh both went much higher, I think. So are you surprised? Think it'll be the same next time? Aluminum foil has a larger amount of friction than you might think. And physics students are always surprised. If you all take physics in a couple of years, maybe you won't be. So, definitely higher. Good. Ooh. That's interesting.
What happened?
When
I
the battery
think-
didn't play with
I think what happened is this right here. See that little kink?
Mm-hmm.
The foil has a kink. So there was like a bigger bump and groove right below the battery. Which
Yeah,
I
that didn't make
hadn't
sense.
seen before. No, it didn't make sense. And I think that kink is why, but we can try it again. I'll in fact turn it around so you ladies can see better. Over here. Okay. And I'll put it where there's not a kink right below it, hopefully. All right, the kink is further down the way now. It'll probably collide with the little thing there. All right, there we go. Battery, Play-Doh, wood, pretty quickly. Oh, yeah, I think, well, there isn't much of a kink there, but yes, I think that the battery didn't go first that one time just because it hit the little kink. So,
experimental error.
yes. Friction definitely is affected by the surfaces that are in contact with each other. You change the surface either by sanding the wood or applying a new surface. And in physics, we stoke the wood and dump baking soda on it, and we try all sorts of messy things to see which one will increase or decrease friction. But if you change the surfaces, all bets are off. Friction is totally different depending on the surfaces that are in contact. So that's about all I've got to say about friction. So last week we talked about Newton's laws. Anyone want to review Newton's first law? Chris?
The object in motion or rest can stay in motion or rest until acted upon by an outside force.
Good, and that's also called the law of
Gravity?
inertia. Talking about gravity like next
Yeah,
next
that's not yet.
module? Soon?
The next
Soon.
module.
Gravity's really, really interesting. And Newton's second law,
F equals ma.
F equals ma, and that'll absolutely suffice for any test definitions. And remember that it really means the sum of all the forces is equal to mass times acceleration. So if you have the force that you're pushing with, and then friction, and then somebody pulling from the other side, the sum of all those forces equals mass times acceleration. And then Newton's third law,
Every action is an equal and opposite reaction.
right, or for every force there's an equal and opposite force. So could you predict anything about this strange thing on your
There's
Coke in here? There's Coke.
We're going to explode.
Is there a reason
We're gonna make it
Can
explode.
you shake it?
That we're going to explode.
We don't need to shake it.
Is there a reason for the Coke thing in here?
Yes.
We
We're
did
not
an experiment when
drinking
we
it.
put it on the side and then like.
Okay, so
I'll take them.
This will be fun.
I thought that one worked. So if we cause the carbonation to all come out of the soda, because Mentos like have this bumpy little surface, and so all the gas like collects and then comes out of solution and comes zooming out. So basically what's going to happen is all the gas plus most of the liquid is going to shoot out this direction, right? So you've got a force. All the mass of the Coke and carbonation is going to accelerate. Mass times acceleration that way. So what can we say about what will happen to the truck?
It'll move forward.
It'll move forward. So if the soda goes this way, its mass times its acceleration is going to equal the mass of the whole thing times its acceleration in the opposite direction. So you have to be able to set those two things equal to each other. The force with which that stuff goes that direction is going to be equal to the force with which it moves in that direction. Newton's third law. For every force,
Are we gonna
there's
get
an
to
equal
do it,
opposite
or-
force. Sure. We'll do it at the end, somewhere out there. We've got to find a nice flat place where our mess won't make such a big. Well, obviously, if I do that inside, it'll be
Do it in the
terrible.
hallway.
Oh no! Oh. It's cold out there. You can watch from the window if you don't have a coat. Or you can see.
It's a square. My brother used
So-
pencil. He had him on the side and then it like went into the woods.
Oh.
Like that was pencil. That's what
They make this little tube that helps you dispense your Mentos without
Oh,
making
yeah.
a giant mess. I don't know how to use my little tube though. It doesn't seem to be moving. Oh, there we go. Okay. Well, that's good to know. But it has different tops so you can see what kind of shape will increase the acceleration to, you're going to have the same amount of mass coming out. If you increase its acceleration, hopefully you'll increase the force. So, let's talk about the study guide and do the eat, and then hopefully you'll be more ready for the test, and then we'll go outside and do Newton's third law. For every force, there's an equal and opposite force. Right, all of the mass accelerates that way, so the truck will accelerate that way. And of course, if you have a small amount of mass going this way, with a large acceleration, you can get a big mass to accelerate that way.